All right, cool. Oh. Sorry, I was just thinking it'd be a horrible April Fool's prank to put like a fake whiteboard up in a room somewhere and somebody just starts to erase it. You really got to put your body into it. All right. Everybody see the lunar eclipse? Did you know there was one? It was pretty early in the morning, so I don't blame you if you didn't. I caught it when it was coming out of the umbra. It was coming out of the Earth's shadow, so it's just starting to peek out. It's nice to catch it when it's fully out there in the shadow. All right, that's one thing, right? So hopefully, nobody obviously did any weird cultish activities under the... Yes, you did? Okay.
No, I just have a quick question.
Sorry.
You know, you said 7-2 is going to be on the test.
7-2 will not be on this next test. Not for this test. Yeah, so if you're online, I don't think I've changed it yet, so somebody needs to remind me if that doesn't happen soon. So then the due date for 7-2 will be the date of the test 3. All right, so let's do this. Let's start with T scores. So you've got your T score chart handy. A real quick word about degrees of freedom. Sounds like a Fox special news report, but degrees of freedom, why is it called that? What the hell? If I had 4 numbers that average to be 10, let me say this again. If I have 4 numbers, to be really specific, the mean is 10. Can you tell me anything about the numbers? Say again?
They might be close to 10.
They don't have to be, do they? One of them could be 1,000,000, the other one's negative 1,000,000, and the last 2 could be 10. Or something like that. 20, whatever. But what do they have to do? The last 2 would be 20. How do you find the mean? Add them up. So add them up. And divide by how many there are, in this case 4, and that would make 10. So what do you get when you add them up? 40, because what do you divide by 4 to get 10? You divide 40 by 4 to get 10. So even though you don't know shit about any of the individual numbers, you know that they add to be 40. You with me? So I can start, I just said one of them could be 1,000,000,000, as long as the next one's like negative 1,000,000,000 or something to kind of cancel it out. You guys with me? So how much freedom do I have to pick numbers? I have n equals 4 here, right? So I can make the first one 7, the next one I can make 15, and the next one I can make negative 2. Can I make the next one anything I want it to be? No, that's the dude that's going to make everything freaking work. Right? So what do I have so far as a sum? 20. So what's the last one got to be? 20. So that it adds up to 40. So they get an average of 10. So how much freedom do we have? In a list of 4, how much freedom did I have? I had the freedom to choose how many values? 3. So the degrees of freedom that I have will always be 1 less than the total number of things I have. Right? And that's why degrees of freedom is known as n minus freaking 1. Okay, good. I at least want to let you know why the hell we call it that. Because if I'm you, I'm like, what the hell? Is this a Fox special news report? Freedom French fries are coming back? Freedom fries. Right? Sorry if I'm treading on your political views, but it's too damn bad. Alright, so that's why it's called degrees of freedom. So now that we're over that, just got to be careful when you're looking up in this chart. You're not looking at n, you're looking at n minus 1. So let's see if we can do this real quick. If I had a situation where it was normal, and I have, what you got, Jeff? 17 things. and I want to be 98% confident. Now, if I want to be 98% confident, what would that look like? Where's 98% going to be? How would my confidence interval sit on there? It's got to catch how much?
90%.
90%. It's going to look like that, right? It's got to be decently far out so that it catches 98% of the data, right? How much data is outside in the two tails then?
2 total, but 1 in each side. 2 total, but
Yeah,
1
two
each side.
tails has how much total data? If there's 98% in there, there must be... 2 tails has 2%, right? There's 98 in there, how much must be outside? 2%. 1 tail would have how much?
1%.
Half of it. All right, let me stop there for a second. Do you guys see now why the T-chart is set up the way it is? Partially. Right. Do you see how it has 1 tail and then 2 tails, right? So everybody looking at their T-chart. You'll see later, when we get into chapter 8, when we start doing hypothesis tests, if I want to test a claim that the mean grade has gone up, it's higher, that would be a 1-tail test. So I would look where it says 1 tail. What does a confidence interval always make? When I draw a confidence interval, it always makes
2 tails.
2 tails. So I can pretty much always look at 2 tails, but if you make a mistake, you look at 1 tail, you'll be fine. What's area in 2 tails is 0.02. That same column says area in 1 tail is 0.01. Do you guys see that? A lot of you guys have not, your gaze has not shifted from me. So you gotta look on the chart. Alright, so area in 2 tails, 0.02. That same column, area in 1 tail is 0.01. They both reference the same situation. Of course they do. They both reference that situation. Now, what's my degrees of freedom?
16.
Good, 16. So now I know how to go down to 16. And I'll look over to that column we were just describing, the one that deals with this. Either way you look at it, you can't go wrong. So then the t-score I would use here would be 2.583, right?
Right.
I almost forgot, yeah. Yes, sir.
Does that say something F?
Yeah, what is this?
Degree of freedom.
Yeah, good. So the way I'm going to write that is DF because too many freaking letters in degrees of freedom. Yes?
What if you have something like n is 42?
You're beautiful. So I want to start off with a nice one. And real quick, what has to be true for me to have to use a t-score? Why were t-scores invented? Why were they invented? To cover our ass for when we don't know
The standard deviation.
the real standard deviation. When we only know S, we don't know sigma. So what's going to tell me to use a t-score is if I have S known, not sigma. If I knew sigma, what would I use?
Z-score.
Z-score, because that's what we've been using before. The t-score is a new thing. When we say, oh yeah, it's more real to realize that I normally don't know sigma. I normally only know S. Okay, cool. What's got to be true in order to use Z-score, though? Has to be normal. Kick ass. It's the same thing for t-scores. So 2 things. In order to do anything, it's got to be normal. And how can you tell if it's normal?
Or they state it.
Say again?
They state it.
Good. I love it. That's the one that people always forget. They just say it is, and then who cares about whatever the hell's happening? If they say it's normal, who gives a shit how big the sample size is? But the second way, if they don't say anything about it being normal, what's the second way?
30 plus. More than 30.
No.
Yeah, it's more than 30, right? For the sample size. Cool. Or if we're talking about binomial, NP and NQ is bigger than 5, but we'll get there. All right, let me stop there for a second. So in general, I can't do anything unless it's normal, which is why we continuously are saying, is that normal enough? Does that look normal? Ever since the very first few weeks in this class, we've been kind of saying that. Does that look normal? What's normal mean? Does that look normal? Is that normal? Yeah, that's what we've been doing. Sounds like a trip to the doctor. Is that normal, doctor? Is that normal? No? Shit. All right, so let's say we have a normal. In fact, let's say I don't even say shit, but I say we take a sample of, like you said, 42. What else can I tell you? I want to be 90% confident. And what else can I tell you? That's good. Do I have to tell you it's normal? No. So A, normal enough because why?
30.
N equals 42, which is bigger than 30. Central limit theorem kicks in and says, okay, go ahead. And then I'm also going to tell you S known, not sigma. So what do I use?
Wait, what is S?
Yeah, what is S?
Sample standard deviation.
Sample standard deviation. Cool. Right? It's the sample equivalent of sigma. So I don't know if you guys remember, way back in the day we were using X bar and S, or mu and sigma. And of course the more formal letters are telling you it's a population. And the less formal is a group of people you talk to. It's a sample. Okay. So then what do I have to use here?
T-scores.
T-scores. In fact, I'm allowed to use T-scores because it's normal enough. And I can't use a Z-score because I don't know sigma. So what's my degrees of freedom?
41.
Do you have 41 on there? No. So you're always more conservative. You always go even further down. So you look at 40. So even if your degrees of freedom was 44, you'd still go to 40. And do you guys see on here, how much do the T-scores change once you start to get up in the 30s and 40s? Are they changing a lot? In fact, look, they jumped from 100 to 200, but did it really change much? No. Cool. I like it. Okay, cool. Maybe. So to be completely transparent, this would not be good enough to use in what's known as the real world. But there are reasons why teachers, me amongst them, use this chart. It kind of helps you, as you use the chart, you get more familiar with how things are kind of laid out. If you don't use this chart and use a button on your calculator, you don't get a feel for how things kind of look. You miss out on something. And this is not a very difficult chart to use. Laura, how you doing? What's up?
I don't get what represents S still. Like, I don't see it in the problem. Like, is it like one of those numbers?
All right, let's do this. Does everybody feel decent about how to use the T-score chart? That was my purpose up here. Let's do an actual problem so you can see how it fits in. And I'll do an actual problem, how you're going to see it worded from me on the test. Right? And that normally gets more attention when I say that, but it's true. I'm not going to use the letter S. I'm going to be evil, because that's the way the world is, right? The world is evil. The world doesn't say, let me put it to you the way you were taught. No, the world just says, here's a bunch of shit, deal with it. Wow, that's such a it's an upbeat view.
Very dark.
I know. But get out there and live. Yeah.
Is T 1.684 for that problem?
Oh, shit. I just erased it.
40.
Yeah, so if you look at 40, and I wanted to be 90% confident. So how much is in two tails?
5 and 5. Total.
How much is in two tails? If I want to be 90% confident, how much is outside? 10%. So 10% in two tails. If you said 5% in one tail, you're still in the same damn column. You guys see that? That's the beauty of this. Either way you look at it, you can't go wrong. So if I go down in that 10% two-tail column and I stop at 40, 1.681.
Yeah.
So my degrees of freedom was 142. What would I actually look at? 100. That's all. Now if it was 199, it's like, shit, just go to 200. Right? But normally to be conservative, to be more conservative, we go down. Right? The less we know, the more conservative we want to be. And that's why T-scores were invented. They're bigger than Z-scores. So they make my confidence interval wider than it normally would be. I catch more shit to cover myself for the fact that I don't know the real standard deviation. So if I don't even know, if my chart doesn't even show me what that is for that, I go more conservative. I go to where the T-score is going to be bigger. I go down to 100. Yeah. Explain what part? Okay, so I wanted to be 90% confident, right?
45 better.
Which means how much is out here? 10%, good. So I got 0.10 in two tails. So which column am I looking at? 1, 2, 3, 4, 5. The fourth column, good. 0.10 in two tails. And then I go down and I stop. The degrees of freedom was 41, but I don't have 41, so I go to 40. And there you see the 1.684.
Oh, yeah.
So T would be 1.684 for that last problem.
Okay.
Cool. All right, so let's see a full problem.
Yeah.
Okay, we take a sample of 36 people and find the mean time spent on Netflix per week to be 3.17 hours with a standard deviation of 1.91. People, when I say, do you use T or Z scores, explain it, people say, well, they gave us a standard deviation so I can use Z scores. Well, that's insane. I have to give you a standard deviation no matter what. I've got to give you one. Which one is this? Is this sigma or is this S? Why? Why is it S? Because it came from these people, the sample, right? So be careful about that. You don't use Z-scores when I tell you a standard deviation. That doesn't make any sense. I have to give you a standard deviation no matter what situation you're in. If I give you the population standard deviation, you can use Z-scores. So I'm going to have to be very explicit. Just like I said on day one, we normally have a sample. So if it's a population, I'm going to have to just tell you the population standard deviation is known to be. I'm going to have to make it really clear. If you don't see that, it's most likely S. So we know S is 1.91. All right, let's see. We want 99% confidence interval for the true mean hours on Netflix. So S is 1.91. What's 3.17? X bar, 11. What's 36? N. Sing it. What's that? Is it where we are? Cool. What's the formula for this? Let's see if I wrote this up here. Watch it. I want you to see. This happens so often with the formulas we use. The formula we used for Z-scores was this. The formulas we use for T-scores is this. Do you see how the formula tells you when to do something, right? When do I use a T-score? When I know S. When do I use a Z-score? When I know, because it's in the formula. I mean, something you're supposed to understand. It's why T-scores were invented, but you can always fall back and say, the formula will tell me what to put in it. Right? Now you have to identify what the hell it is. This is S. So I know I have to use this one. Now what do I not have yet? Yeah, I got X bar, I got S, I got N, I'm just missing T. That's all I'm missing. So what's my degrees of freedom? 35, is that on the chart? Yay! Where am I going to look? I want to make a 99% confidence interval. So how much is out in the two tails? Good, 0.01. 1% in two tails. So how much is in one tail? Two tails is 0.01. How much is in one tail? 0.005. Half of that, right? And you guys see the very first column, 0.01 in two tails, 0.005 in one tail. They both reference the same column because you're saying, hey, dude, this is the same freaking situation, right? Does that make sense? If I have 1% in two tails, I must have 0.5% in one tail. Bam! That's why it's the same place. And then I just go to that column because that's what this tells me. And then I stop at 35. So again.
Oh, I didn't see it.
So what did you guys get? 2.724. Kick ass. Let me know right now if you're not able to see how to get that. Can everybody get that? All right, I'm going to take you at your word. Everybody can get that. Good. That's all you got to do. That's it. Now, obviously, I'm not going to give you something on here that's not on here. If I wanted to make a 93% confidence interval, can't do it with this. Because how much would be in two tails then? 93% confidence? There would be 7% in two tails. Is there any 7% up there for two tails? No. Okay, cool. Just has limitations, but in reality, we almost never use freaking 93% confidence interval. Almost never. It's almost always 95, to tell you honestly. But here, for some reason, we went 99%. We want to be even better. So where do things go? Using my formula now, what's this going to look like? Good. 3.17. Give or take. Let me say 2.724. 1.91 square root of 36. Yes. So start here, go up and down this many steps. Why do we still have to divide this by square root of n? That's where people freak out. Yeah, this is a standard deviation that's good for what?
That group of people.
Sample. Individual.
Good, thank you. This is a standard deviation that's good for individuals. From a sample, sure, but it's still a standard deviation that's good for individuals. We need one that's good for groups of 36. We still have to divide. So when you divide this by square root of n, you aren't making a sample standard deviation. You're not. You're making the standard deviation of the population of all samples of size, whatever. And then it would be the one that, so now it's good for groups of size n. So this is still a standard deviation for individuals. I still have to divide it by this to make it the one that works for groups of size n. That's what that conversion does. It doesn't take population, make it sample. No. It makes individual standard deviation becomes one that works for groups of size, whatever. That's what that thing does. All right, so Harry Potter kind of way, I don't know. All right, so what do you calculate first? What's my suggestion here? What do you calculate first? Good. You do the error first. How much you're off by? Somebody done that yet? 0.867. So I'll say 87 is fine. Sounds about right. Stuff is like, it's right. I know. And then you just subtract it and add it, and you're done. Almost done. You have to write the little thing with you. So what's my confidence interval going to look like? 2.3 up to
4.04.
4.04. Come to 3. So take a minute and try to write the conclusion.
Oh, yeah.
before I go there, what would the conclusion be here? We are farmers. No, we are. Sorry, every time I say that, it's like in my head. We are 99% confident that the interval 2.3 to 4.04. Good. Hours.
I would say per week.
No, we'll see. Well, you'll eventually have to say it. That the interval blah contains the true mean number of hours per week spent on Netflix. That's good enough for right now. Cool. So I really want you to, the very first time we were doing confidence intervals, they were based on z-scores, and they were based on formulas we'd done before. All the work and the final conclusion are exactly the same. What's the only one thing that changed is the number I put there. And why is this number not the number it would have been for z-score? It's a little bit higher because I don't know the real standard deviation, so I got to cover my ass for that, so I make my net a little bit bigger. If I'm like, how far does that fish get away from its home? I'm not sure. I think it's this. Well, let's just throw a little bit bigger net just to cover our ass because you don't know what the hell you're talking about, child. Does that make sense? I don't like to fish, but the analogy is really nice. All right. Maybe just for me. So I want to show you. I think a while back I said, if you go to Google and you type in the word study and you change the search to the past week, it's a decent way to get really quick hits on studies that have been released. And normally they kind of suck. They're like Yahoo. Basically, anytime I see something on Yahoo, I'm like, well, I don't want to look at that. But I go there and I immediately click on the link to the actual study, so I don't have to look at crap. I'd rather look at the actual study. So this is kind of neat. I don't know if you guys saw, I kind of went quickly. This is how using the internet makes you think you know more than you do. So they actually did a study about this. And you're like, did my tax dollars go towards that? Search it and you'll feel like you'll know. I just want to show you some things in here that should look familiar. So look here. I like this. Look at this little section here. Right in here. This very first thing under results. So they did this little thing, and they talk about the background, they talk about what they had the people do, and they talk about how they differentiate to people that didn't use the internet versus who did, and how they figure out who thinks they know more, and all that kind of stuff. They have that whole backstory. But now they're telling me it almost doesn't matter what the situation is. During the induction phase, rate themselves as being able to get significantly better explanations, blah, blah, blah. So here we got the mean, the standard deviation. And look here, 95% confidence interval, big halves. Bam! This is an article that was admitted to this journal that Yale freaking did, and that's stuff that we would do right now in this class. So it's always nice, especially in math, to show you guys there's a problem you could do that's actually sitting in a freaking article in a journal that's a real study. And one little thing else, look at this guy here. This is that same little thing we've been looking at ever since day one. Does this mean that the results are significant or not? And everybody always keys in on it's such a small number, but that's actually what exactly tells you that it is significant. The probability that this would happen randomly, that there is no effect, what they're looking at, is so small that what's more likely is, yeah, this didn't happen randomly. This is actually an effect. That's the whole point of that. P's got to be less than 5% right now, and Chapter 8 will vary that, but less than 5% tells you it's significant. If there's an 80% chance it's going to happen anyway, You know, if I'm like, well, if you drink my special juice, you'll feel better. And then you do a study, and 80% of people would have felt better anyway. It's like, your juice is crap. Get away from me. Right? But if I do the study, and like 0.1% of the people would have felt better anyway, but they all said that they felt better, holy shit, your juice made them feel better. Wow, that's significant. You guys with me here? So, you'll almost, they definitely have to give you the p-value so you can see for yourselves how significant it is. For other things, there might be, let's see if there's a different thing. P less than 0.001 is like, holy shit. A little bit later, I think they have a p of 0.05, so you can tell if for yourself is it good enough or not. Here we go. P less than 0.05, so it's still decently significant, but not as significant as it could be. So look here. This was the two groups they used. They did an initial study to see their differences, and P is 0.99. So any differences that are in there are just due to randomness. It's a 99% chance. And look at the confidence intervals. Look at this. Here's the confidence intervals. Do they overlap? Yes, they totally overlap. So going in, people had the same kind of impression of what they knew. After they did the study, look at the confidence intervals now between the two groups. The one group that accessed the internet and got some stuff, and the other group that, I don't know, maybe accessed an actual book. I don't know what they did. I didn't really read through this. I just found it a minute ago. Look at the difference between the groups now. Do these overlap?
No.
That's evidence that they are different. In fact, the probability that that difference would have happened randomly, that's less than 5% chance. That's decent evidence that that change is because of what they were looking at in the study. That's how that works. That p-value is huge. So anytime you look at a journal article, in any field you're going into, there are journal articles written about that field, and they will eventually have p-values in them to show what's going on, to be evidence, to show evidence that something's changed because of what they're looking at.
So what you're saying is that P is the relationship between the two variables?
So here's a good example. You ready? All right. This is actually, I stole this from the book a little bit, but I don't care. So let's say that there's a certain average grade people make on the SAT right now. I think I've used this before, but let's just do it again. And I do like a 1-week study session. And I take 120 people come and take my study session. And then they take the SAT. Right? I do a statistical study. They get a higher score. In fact, I find the p-value to be 0.03. Is that significant? Yes, it's less than 0.05. It's decent significance, right? Depending on who you are, but that's pretty good. That means that the score that those 120 people made, what's the chance that it just happened randomly? I just happened to randomly have 120 smarter people come. They would have made that score anyway. What's the chance of that they would have just done that on their own anyway? 3% chance. So what's more likely is that my course actually helped them get ready for the test. There, that's it. So that's anytime you see a p-value, it's got to, it doesn't have to be because there's other uses for it, but the main thing it's used for is, what's the chance this would have happened randomly? Right? So there were differences. I really want you to see. They actually looked at the differences between their groups beforehand. You know, like if you do a drug study, you want to make sure that your control group isn't made up of a bunch of people that are about to pass on. And then the other group is a bunch of people jumping around and doing calisthenics. That might skew your results. You with me? You want both groups to be sort of the same representation. So this is saying that any differences between the two, 99% of them are due to random differences. All right, that I can live with. That means that they're really just about the same freaking group, right? Are you guys kind of with? And then after I run this thing and I do different things to each group, the probability that the differences between them are due to randomness is less than 5%. So what's more likely? The differences between them are due to what we did to them, or what we had them do. Yes, ma'am.
So if it's 5% and lower, it's
Right now. And I want you to realize, what was the example? I wish I could remember the example I was given earlier. Who was with me? I was talking about, like, we'd hope it to be, oh yeah, the elevator thing, right? For an elevator to be safe, there's a problem in the book about a certain number of people on the elevator is going to make it plummet or something. And it's like an 11% chance that could happen. And you're like, that's not good enough. We want that to be really low. In fact, 5% is not good enough. If you're like, that elevator is going to kill you 5 out of every 100 times, I'm like, guess what I'm not going to do? I'm not going to get on the damn elevator. I'm like, you know, that's like decent odds, but, 100% chance, almost 100% chance I'm not going to die if I take the stairs. I mean, there's still things that could happen to me. Versus 5% chance you're going to die in the elevator. You guys kind of with me? So that 5%, I can control it. Right now you can't, because we're not to the point yet where we're going to study that. But in chapter 8, we're going to start to vary that. And in fact, to be honest, we're sort of doing it already. When I'm changing my confidence interval to 99%, I'm sort of making it 1% now. Accept that what's unusual, right? So we're sort of doing it already, just not very explicitly. Right, chapter 8 will be very explicit. We'll say 1%, that's what we want to set it at, and then do our study. All right, maybe. Oh, it's a lot of shit coming at you. So, I mean, one thing I want you to realize that I point out here, and that happens in the homework a couple times, is you could make 2 confidence intervals. In fact, sometimes I'll do this, maybe, for a class work, I have people do like men and women, and you do a confidence interval for men's grades, so maybe be like from 70 to 83, and a confidence interval for women's grades, and if it just happened to come out to be this, is that evidence that the women's grades are higher than the men's grades? Yes, right? Now, I'm not telling you a lot of shit. I have to tell you, if this is a 1% confidence interval, then screw you, Jeff, right? So it's not. Let's say these are both 95% confidence intervals. You with me? So the chance that I'm wrong about either one of them is about 5% chance, right? Now, if I got one of them was 70 to 83, and the other one was 80 to 92, is that evidence that the averages are different? Do they overlap? Could the averages be the same? Yeah, what's the highest the men's could be, according to my study? 83. What's the lowest the women's could be? So they could be the same. So this is not evidence that they are different. So that's why showing the confidence intervals is really nice. It's actually not good enough by itself, but you can see that they don't overlap. The confidence interval for the control group versus the confidence interval for the people that they had do whatever it was they were doing. They don't overlap. So that's evidence that they're not the same. That's evidence that something is different about them. Yeah, that's one immediate thing you can do with confidence intervals, is make 2 of them for 2 different populations and then see, is it evidence that there's a difference? Okay. All right. So let's do the formula sheet, and then we'll do whatever else you guys want to look at. So as long as you didn't lose any points on your first formula sheet, you can bring it. So all the same stuff you had on the first formula sheet, you can use all that again. Right? You can bring as many pieces of paper as you want to. They can be as large as you want them to be, as long as it doesn't annoy anybody around you. You guys with me? So you can have a giant one, just put it up against the wall, and people actually will like it if the formulas are written correctly, because they can just look at it. Right? I don't care. I don't make you do like a little. I'm not that evil yet. Yeah. But the thing is, there can only be formulas, and they can only be the formulas that we agree upon right now. You want to put anything else on there, you better tell me right now. So what do we got? We got. Obviously, you want to put these down. Right? Do this in black. All right, so let's kind of go through this. There's not going to be any chapter 4 stuff. I've decided to not put box and whisker. That's just a little far back. We'll do that for the final, so we'll review for the final. Yes, sir?
So 3.4 is not going to be able to.
No. I decided that's a little bit too off the mainstream. We'll do that for the final. So starting with chapter 5, you've got stuff like this here. Alright. And then chapter 5, so that's with the probability distribution, the general probability distribution, where they give you x and p of x. So again, the formula kind of gives it away. When do you use that? When you've got those things. Then what do we know for binomial, the probability? And then, of course, the two best formulas ever for the mean and the standard deviation, what are those? For binomial. NP, good.
Square root of NP cubed.
Kick ass, right? That's the best, man. Everything else was disgusting. That's chapter 5. Sure didn't leave anything out. Chapter 6, of course, uses this from before. This is actually introduced back in chapter 3. But then chapter 6, the only kind of new stuff chapter 6 does is like this guy here. Now, please, dear God. Please, dear God. This is not sigma divided by x or some weird shit. How many symbols are right here? 1 is sigma sub x bar. It's the standard deviation for the sample means. And if you want to, just to really drive it home, s x bar is s over the square root of n. So that would be a reminder that you have to do that even if it's s. You still have to change it to a standard deviation for groups. All right, let's see. What else was in chapter 6? Blah, 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 blah. This is not a formula, so you can't write it down up here, but what's got to be true for binomial to be normal enough to use the NAB? NP and NQ are at least 5. Yeah. All right, or greater than 5. I can't remember this book. 5 is kind of like the dividing line somehow. Right? But you can't write it up here. It's not really a formula. It's a condition. It's a requirement. And you must know that. Cool. All right. Let's see. What else was there? Am I forgetting anything? Chapter 7 is where we had the big ones. We had this guy. This guy, of course. And then this guy, if you remember. When we get to 7.2, there will be 2 more equations that we'll learn dealing with proportions, but we're not there yet. Anybody have anything else to suggest in addition to this?
What's E for the last one?
Yeah, what is E?
Error.
Error. So this equation you would use if they ask you to figure out what? The sample size. They say how big of a sample, or how many people would you have to talk to, or how many shoes would you have to measure to be within, and that key word within, to be within so much, plus or minus the error. Within 3, so the error is 3. Coolness. Now, I don't know if you guys, in the textbook, they always write this 2 things. All right. I always forget about this because it's just so damn silly. But the textbook's got this symbol here. Right? And let me ask you, it's got Z alpha over 2. Now one of the homework questions asks you what that means. Z alpha. So if I had, for example, if I had Z, I don't know, Jeff, 0.11. Somebody know what that represents? Yeah. Sort of. It's a z-score with an area of 11% to the right of it. So this would be z.11. It has 11% above it. So the book kind of goes through that. I hate that notation. It's just silly because students see this and they think there's more than one thing. It's z times whatever that magical little fish dude is, and then divide that by 2, and that's bullshit. So what the hell is this thing all about? When I make a confidence interval, I want to be, let's say, 98% confident. Well, how much is outside of there? 2%. That's what alpha is. Alpha is the amount outside. Always. It's kind of silly. Alpha is just the amount outside. So if I wanted to find the z-score, what area is above it? What area is to the right of that z-score? Half of the little fish dude. Little fish dude's 2%. Half of that is 1%, and that's why that symbol is what they put here. It's the z-score that goes with your confidence interval. But why do you need a stupid little subscript for that? You just know that's the z-score you need for your confidence interval. So it doesn't look like there's more stuff in your equation. But I always forget to say that. I'm like, that's just so silly. But oh, too bad for me. So I want to make sure I say something about that. And the thing I was about to say was, the book writes this stuff as this, and then they tell you later that error is this. I forget. Right, that's how the book writes that. If that somehow is better for you, cool, you could write that, that's fine. That's an accepted formula. So you can write this the same way for that. Now, if you don't look at it like this at all, don't write that down. Don't do that to yourself. Don't put something you're not used to on your formula sheet. Yeah.
Was there anything you don't want on here?
Anything I have not written up there
Oh.
cannot be on there. It's that simple, right? That's it. That's why I'm saying if you think something else should be up here. Now, of course, you could use anything that was allowed to be on your first test formula sheet. You can bring all that shit with you if you want to. There's very little on there that will help you, but you can have it. And you can have all this stuff that's on this middle board here. That's why I went over there for this, right? This middle board is the formula sheet. Anything else that you want to say should be on there. Okay, cool. That's it. So if you have anything that's not up there on your formula sheet, or that was okay for the first test, you're going to lose points. All right, so don't do that. Don't make me be that person. Right? I will be that person. Because that's what you need if you do that shit. Yes? Well, I mean, this was on there, but you can write it down again. But if you just like, you can make a little collection so they can have all of them for the final exam. You with me? You can just bring all your formula sheets for the final exam, or you can make a fresh one, whatever the hell you want to do. Right? It's totally up to you. Okay, so that's formula sheet. And where do you guys want to go from there? What do you guys want to look at? Remember, number 7 is not on the test, right? For the number 7 on the practice test. Let me go ahead and give you the answer key. Unfortunately, I had to Frankenstein it together from a few answer sheets from the past. We'll see, hopefully this makes sense. Someone here? Or is that? Go over wherever you want. Number 7.
Okay, yeah. He said for these problems he would give us a standard deviation, right? No matter what you needed. This problem, it just gives you the data, so I'm assuming it just solves like the same way you would calculate any kind of standard deviation. So it would be x minus mu squared, right?
I think so, yeah. Oh, yeah.
take the square root of that.
So,
Oh, and divide by x.
Oh. Mhm. I forgot to tell you guys the average on the quiz was an 81 almost. The standard deviation though was a 17, which is kind of big. It's because, well, there were 17 A's, quite a few hundreds in there, 13 B's, then 4 C's, 5 D's, 6 F's. And some of those F's were on the very low side. So that's why the standard deviation is so huge. So it really was a you know it or you don't situation. So the nice thing is, the only nice thing that's possible about getting a really low F is because I have to believe it's because you haven't done the homework yet. So, and that's why I do what I do. The quiz kind of goes, oh shit, you should really have done your homework so you could do this. And if you didn't, then the test, you do the homework, you do better on the test, you make correction to the quiz, and the grade goes up twice. Kick ass. I mean, that's the way it should be. Your grade should reflect what you know. If you just didn't know something at a certain time, that shouldn't kill you for the rest of the class. That's why I do that. So don't immediately give up hope if you did bad on that quiz. Just make corrections. Do whatever you haven't done so far to correct why you made such a bad grade, and then just do better on the test. That's all. And then your grade goes up. Yeah. So you get 1D.
Yeah.
Why didn't I use? X equals 12?
Yeah.
So if I go, so the mean was 5.91, right? For number 1? And then the standard deviation is 3.316. So if I go up and down one standard deviation from 5.91, I go to 2.5 something to 9.2. Is 12 in those? So I only pick the ones that are in there, and the only ones that are in there are 5 and 6.
So you only look at X, you don't look at X squared.
Definitely not.
That's what I
Yeah.
tried to do.
Yeah, no.
It's gonna bug me. I want to figure it out.
So guys, look at number 1 real quick. What's the probability that I pick an 11? If I just pick one of these, I pick 11. What's the probability I get 11? 0.192, cool. Not 2.112. Not those. The only purpose for those 2 columns that you create is so you can get the mean and the standard deviation. That's the only reason they exist, right? Questions about probabilities of those numbers, you can totally answer with just the first 2 columns, because that's where the probabilities of the numbers live. So when I go within 1 step of the mean, I just say, who did I catch, and what percentage does that represent? So I caught all the 5s, and what percentage of the data are 5s? 0.352. And I caught all the 6s. And what percentage of the data is that? 0.154. So what total percentage of the data did it catch? Add them up, I get 50.6%. Does it sound like it's normal? What should it be if it was normal? Within 1? We've already forgotten? 68%. Cool. I like it. Yeah, like empirical rule, that's so 15 minutes ago, John.
Can you go over number 5?
So number 5. Oh, yeah.
Or stage 5?
Okay. And notice how there's 2 parts to that, right? So for the first part, n is 24.
Yeah, but
For the second part, n is 356, right?
oh wait, no. I'm sorry.
That's the one mistake people make a lot. Is that part of what happened? So that's why for part A, the mean and standard deviation are kind of big, because now my n is 356. I would have thought we would have trouble with 5.1b. The probability of x less than 22. Why would that so desperately suck?
What number is it?
This is a 5.1b, right? A practice test is like a legal document. Section 5, subparagraph 1, part B. Oh yeah, I gave out the answer keys. I'm gonna be bleeding students.
That's your answer.
What's less than 22? 21, 20, all the way down to 0, right? 0 is the least successes I can have. That would, so I don't want to do probably 0 plus probably 1 all the way to the probability of 21. I don't want to do all that. What's the opposite of less than 22? What's the opposite of less than 22? The word more is not good. The word more is not good. I don't have a problem with the word more itself, just in this case. Greater than or equal to, yeah, because does this include 22? Does this include 22?
No.
It's less than 22, so the opposite better include 22. 22 has to have a somewhere to go, poor little dude. So this will be, that's why I do what I did. I do 1 minus the probability it's 20, greater equal to 22. Probability is 22, minus probability is 23, minus probability is 24. That's what I do for that problem. If you see, that's the problem I thought would give you guys the most trouble. But anytime I ask you a probability question and the opposite situation has less work to do, hell yeah, I'm going to do that and then just subtract what I get from 1. So does everybody see why it's this? This would be 1 minus the addition of all this stuff, right? Probably x greater than or equal to 22 is 22 or 23 or 24. And then I just distribute the minus. Or add all these up and then subtract what you get from 1, because you want the opposite. That's the opposite question I've asked you, right? Okay, that's enough for that. So that at least one thing that I harped on so much is just one possible thing of a larger idea. Whenever the opposite probability has less work to do, yes, please, I will do that. Thank you. Okay. You guys look like you want to jump me after class. Took your stat stuff, too. I try. All right. Number 4 has got some weird stuff to it. 4b really is the weird one. But I wanted to give you that kind of problem just to show you how that would work. Do you see how that relates to 4a, number 1? In 4a, number 1, you figure out the probability that somebody scores more than 315. Right? So if you work out that this, I can't remember, I think it was, what did we figure out? So number 4a1. I get this probability as 0.1635. You guys kind of with me? How do I interpret this? What is this? How do I say this in English? And the situation is, number 4 says, California school students taking it. This is the mean score. So this would be getting a mean score of more than 315. So how do I interpret this? The most direct interpretation is it's a probability. So there's about a 16% chance that some student will score more than 315 on this test. You with me? What's another way to interpret that? This 16%. What's another way to interpret this answer that I get? Good. 16%, about 16% of students will score on the test. So in part B, I say, if I had 2,000 students, how many would I expect to score more than 315? Well, 16.35% of 2,000. That's why I multiply. Isn't that n times p, actually? But it's really the larger idea of what does a percentage mean? The percentage of a total is the subset that do that thing, right? Maybe. So what percentage, how many would you expect to score between 274 and 292? You take your answer to 4A number 2 and you multiply that by 2,000. That's the percentage of students that would score between those two. Because we all know this. If 10% of the people in here right now are left-handed, what's the probability I pick a left-hander if I pick somebody random? All right, we know that when I say there's a 10% probability of something, it's the same damn thing as saying 10% of those things is that. Right? 10% of all dogs can't turn left. Sorry, right? It's like, don't believe it. Okay. If 10%, just to make something up, just so that maybe this will just happen, somebody's going to actually believe this. One of my teachers told me that. I'm pretty sure it's right. 10% of all dogs can't turn right. What did I say? Left. What's the probability then, if I pick a dog, that they can't turn left? 10%, right? I mean, those are the same thing. Those mean the same thing. So I can interpret this in those two ways. There's a 16% chance that a student will score more than 315. That's actually the less good way, the less desirable way to describe it. It actually makes more sense to say 16.35% of all students will score more than 315. I can use that, and that's why I wanted to put number B, part B on there, so I can use it that way. If you got 2,000 kids, how many are going to score more than that? 16.35% of 2,000. We did that with the Mensa problem. Mensa wanted to open their chapter up, and they said whatever percentage have an IQ more than 133. So many millions of people, how many people will be eligible to join us? That percentage of whatever millions. Same problem, exactly the same problem. What's 5C mean, that bold stuff I have? What's 5C all about? What about it? What's it mean? What do I have to do? True. That's any normal problem I'm going to try to figure out the area under. But what's the main idea with the NAB? What's the adjustment that's made? No.
You're making the number that you're working with to be continuous.
Continuous, beautiful. So I got to use a continuity correction. Yes. All right, so when you see me, I'm so nice nowadays. I mean, when I first started teaching statistics, I just gave you the problem. I didn't say NAB, I didn't say shit, but now, nothing against you guys specifically. But people are just less able to handle this. But I'll say the NAB, and what does it mean when I say NAB? That means I'm going to take the number I'm giving you and adjust it up or down by. So what do I do? If I it's number 5. Number 5 is all about adults. You can have 24 adults, 87 adults. So what kind of variable is that? Discrete or continuous? Discrete, good. We're not continuous. We don't flow into each other. Well, I think this is me, but it might be him. No, that's some weird shit. We're all just connected. You ever seen that movie Society? I think it's called Cronenberg earlier. Don't watch it. It's freaky. People flowing into each other. So number 5 is all about discrete data. So on 5 part 2C, it says what's probably that at most 340 adults. So I draw this because before that, part B, I ask you to check NP and NQ. And what's got to be true about NP and NQ? And if that's true, what does that mean? Normal enough. Kick ass. So in part B, we know it's normal enough. So I draw that curve. But what really wants to be over the 340, considering it's discrete?
340.5.
Well, what wants to be over it? A continuous thing? No, it wants to be a blocky-ass discrete thing, right? Old Nintendo game, Pixels. Not continuous, it's nice blocky 8-bit. Hello. No? Okay, all right. So, and this is what you're saying, Keisha. This will be, so if I want more than 340, do I want to include 340? I think I say more than 340. No, I'm sorry. I say at most. So what's at most 340? What's that mean in math? 340 or less. At most 340. I can't let it get above 340. So it's less than or equal to 340. Now let me ask you, do I want to include 340?
Yes.
Yes. And I'm going to shade which way? Down. I like it. So do I want to start there or here? Here. Kick ass. Because I want to include 340. So what number am I going to use? Not 340. I'm going to use... I'm going to make a z-score out of that. That's the continuity correction. So when you do all that weirdness, when I say use the NAP, the normal approximation to the binomial distribution, right? I know there's a lot of information in this class. I know it because I've said all of it up to this point. But I desperately try to give you guys triggers about when to pull out what. And the more you understand why we do this kind of thing, the easier it is for you to remember when to do that sort of thing. Why do we do that? So it runs into the next dude, the 341 bar, and then it looks continuous. That's why it's called a continuity correction. It makes us pretend like it's continuous. Everybody runs into everybody else. That's why the analogy wasn't just me being silly, but if you actually connected to the next person over, we'd be a continuous thing. That's enough of that. That's weird. We wouldn't be discrete people. Yes?
So every time that we see NAB, we use 0.5, right?
For this class, because your teacher's being nice. In the real world, you just have to know. Yeah. But it's anytime you're trying to use z-scores to talk about discrete data, you've got to use some kind of an adjustment. For a binomial situation, it's the continuity correction, the 0.5 thing. Right? There are other distributions we could use, but yeah.
Where's 3B?
Say again?
3B
Where's 3B?
on our...
Oh, I think I just gave them, there's a find the z-score with 91% below it, and find the z-scores bounding in the middle, so I just called it A and B. Just to make it clear, this the two parts. On the actual test, I would make them actually A and B, and people still forget to do one of them. All right, make sure you answer every question. Yeah.
I understood the first part of 3, but not really the find the z-score bounding in the 91%.
Yeah, what does it sound like? If I have a normal distribution, so I tell you in the build-up that it's a normal distribution, right? The middle 91%, so it's got to be around the mean, the middle 91%, that sounds like I'm making a what? What does it sound like the first step in creating? Confidence interval, right? I want to be 91% confident, but I'm not making a confidence interval. I'm just saying, can you find the z-scores that would go here and here? And that would be the z-score you would use in the formula if you actually were making a 91% confidence interval. Cool. Yeah.
Can you show us what we would do for the rest of 5C? Because I'm lost.
And before I leave this guy, so 5C next. Is that this guy? Oh, yeah. Before I leave this dude, how do you find those? Do you look up 0.91 in the chart? No, the chart doesn't know a damn thing about the middle something percent. It only understands below. So what area is below this z-score? Beautiful. 9% outside, 4.5% on one side. If you look up 0.045 in the body, because that's an area, you try to find the z-score that's related to it. That'll be there, and then that's just going to be the positive same number, right? I like it. And before I get too far, I'll come back to 5C in a second. If you look real quick at your T-chart, Do you guys remember some of the z-scores, like for a 95%? Maybe we haven't done enough of that. That's 1.96. 90% we've done a lot of it's 1.645. Do you remember that z-score? You start to remember z-scores. Don't worry. That doesn't mean anything bad's happening to your brain. Not necessarily. Look at the very bottom where it says the degrees of freedom is large. I love that. It's not defined. It's just big. Those are all z-scores. So the very bottom of the t-score chart are z-scores. So if you need to make a 98% confidence interval and you can use z-scores, 98% is 2% in two tails. You go all the way to the bottom. 2.326 is like 2.33. That's the actual z-score we used before. It's just a little more precise. That's kind of kick-ass if you let it be. So if you stop, you'll get a t-score. If you go all the way to the bottom, you get a z-score. That's a double-purpose chart. That's kicks-ass. So it puts a little baby chart. Remember in the corner of the z-score chart? A little baby. That's baby. That's baby shit. Here's the teenager, right? Because this is still not quite all the way there, but still, z-scores there at the bottom. Now, finally, I can answer the question. So on part A of 5.2, you have to figure out the mean and the standard deviation, right? Kind of makes sense. Because on this part, I want you to figure out z-scores, and you can't figure out z-scores unless you have these two things. So to figure out the mean, that's n times p, and the standard deviation is np cubed. So you should all be able to just plug and chug. So you can see on 5.2a, I get 313.28 and 6.131 for those. Is that cool? Just plugging this stuff into the equation. So then what's right in the middle of this picture? 313.28. That's the mean. So how do I make this now? This is a continuity correction. It's not 340 anymore. We're going to make 340.5 into a z-score. And I like doing it this way. I'll ask you, like on one part, I'll say find the mean and the standard deviation. I'll ask you in another part, check NP and NQ. And then I'll say use the nav. Well, you've got the mean and the standard deviation figured out. You've checked to make sure it's normal. Bless you. You just have to now do the continuity correction. And then I make a z-score out of this number. So just like central limit theorem says, before you go making a z-score, change this dude. And then use the same formula, just put the new number there. This says the same thing. It says before you go making a z-score, change this dude. Don't put 340 in there. Put the adjusted number in there that's going to make your approximation better. This is an approximation always. Because it's not a normal distribution. It's a freaking binomial. But it's normal enough. The approximation should be good. Eternally hopeful. Right. So then how do I make a z-score? I get 340.5 minus 313.28 divided by 6.131. Right, that's my adjusted score. The mean, the standard deviation. I think I get like 6 point something. 5 point something more. Oh, 4. Okay, so with something earlier that's 6. So this is 4.44. And the question is, at most, 340. So is that on the chart? The chart goes up how far? 3.5. That's 4.44. That's off the chart. So you can either say what the chart says, or you can say what's actually more correct. The chart says that's 0.9999. What's actually better is this is approximately 100%. It's like the other side of 0 plus, right? I guess it's 100 minus. I guess it's almost freaking 100%. Just imagine if your height was this z-score was represented by this 4.5 standard deviations above the mean. How many people are taller than you? Basically nobody. What's probably going to run into somebody taller than you? Basically 0% chance. So you are taller than basically 100% of the people. Okay. It's like a raptor teaching. Clever girl. Alright. I haven't gotten much sleep. Alright, you guys look properly oppressed. Doing a good job. Pretty much. What kills me, and I forgot to do this for you, actually I didn't have time, but this morning for my 176 class, I made a little chart for them showing the number of homeworks that people had done versus their grade, and it was basically, and then I kind of fit a little line to it, and I showed them this. I mean, it's silly. I can make one for you guys, I can make one for anybody, basically almost always the same thing. Chapter 10, we'll be doing this kind of thing and figuring out how strong that relationship is. But I mean, it's the number one thing that's killing some of you guys is you're just not doing the homework. Or you're sort of doing the homework, but you've gotten your hands on a solutions manual, and it's doing the work for you, and that's complete shit, right? I kind of think about it like you go to a camp for basketball. You want to be better at basketball, right? So then, and you're supposed to videotape you're at home. You're supposed to videotape yourself shooting free throws and dribbling and stuff. So you have a friend of yours that looks like you come and do the videotaping. What the hell sense does that make? What? I mean, that's essentially what you're doing if you're just taking your answers from somewhere else, right? And a lot of you guys are doing your homework honestly. You're making good, honest mistakes, which is going to be expected. I mean, it's just the way it is. I don't want you to be perfect. That normally means it's not coming from you, right? I want you to make some mistakes so you won't make them again. If I don't see those, I can't help you. It just kills me. It just really kills me when I can't help you get better if I can't see why you're not as good as you could be. You give me false representation. All right, enough of that. Sorry. It just kills me. And then some of you guys are like, people have the solution manual? Where are you? Who's got that? Somebody does. Yeah. If you don't have any more questions, you don't have to sit here and stare at me. But if you have questions, ask away.
It make you feel uncomfortable.
Yes.
Judgmental eyes. I'm not sure when do you change the mean?
When do you change the mean?
Yeah. When do you look for the true
I
mean
just have
or
section
the
3 to do. And then I'll
Confidence intervals, or when they say that phrase. Class isn't really over, by the way. We've got a question on the floor. Give me a second, everybody. Do you guys have questions, or you just turning stuff in? What's up? Just get the right Z-score here. Oh no, the problem here, they all add the 1, but they all have to be between.
Oh, okay.
Yeah. Okay.
Thank you.
Oh yeah. Sure.
I was wondering, you checked this, but I don't know if this one's checked.
Oh, probably not.
Turn it in.
Yeah.
Okay.
It's up to you. You can keep it if you want to look at that and do something with it, or you can just give it to me if you want me to. Either way, because you have until Wednesday to. You won't be late yet.
Okay.
Yeah,
All right.
but I didn't. You're right. I didn't even see that. Okay, cool. Thank you.
I did the quiz because I was late. This is the quiz.
Can you do what?
Oh, I get the quiz back because I was late.
Oh,
Thank you.
sure. All right. So your question is second. These guys is first. Okay.
Can I turn in a quiz correction?
Yeah. 6, 7, which one?
6, 7, 24.
All right, let's see. Let's see. Sample 250.
You said correct and you just want to correct it, right? You want to correct it? It says correct on it for the homework?
Yes, cool.
So we have to redo it?
No, just correct the ones that are wrong.
Oh,
Yeah.
gotcha. Okay.
Cool.
Just wanted to ask you about this one. So you talk of 8 points just because I didn't draw that little thing.
Well,
graph.
not drawing the picture made your answer wrong. So that's
I know,
my
but-
suggestion is to do that.
So I still have to do 1 minus this number so to get the other number, right?
Yes, good.
But like you took 8 points.
Yes, it was 24 points total. There were 3 parts to it, and you missed 1 part. So that's 8 points.
It's kind of not fair on 8 points, right?
No, it's totally fair. What I love is when teachers do 20-point quizzes, and students get 12, and they think that's not too bad, right? But 12 is 60%.
Yeah.
So I don't do out of 20 shit. I do everything out of 100. So when there's only 4 problems on the test, or whatever it is, they're each going to be worth 25 points.
Exactly.
Yeah. So you missed a third of that one. So that came out to be 8 points. Yeah.
I have a question.
All right.
Okay.
Let me do this one.
Oh, sorry.
All right, guys. So see, 250. So they got. Oh, okay. So they give you that. The P for the whole U.S. is 67%, right?
Yes.
Right. And then the percentage they found from the sample was 70%. So that's what we're going to use. This is kind of like in the background, and we're going to kind of compare that. What we got from this 250 was 70%, right? Okay.
So,
And we're checking to see whether the 67% still sounds like it's right. So we took a sample to get a feel for if the number that we think is true for everybody really is true. How we doing? So the 250 were randomly selected, so they should represent the population. So they want to see, is the 67% rate too low? So what we really want to do, we have to check and see if it's going to be normal, but we're pretty sure it is. How do I check that real quick? What do I check to make sure it's normal enough?
NP and NQ are greater
Good.
than 5.
So NP, 70% of 250.
That's 175.
And then NQ would be the rest. So it'll be another 75. How we doing? Okay, cool. All right. And so we already know the mean, which is awesome. What's the mean? 175 kick-ass. What's the standard deviation?
And 7.2457.
wait, that's the way of checking normal enough for what kind of problem is this?
I just want to be on the video.
This is for a binomial. We're trying to
Okay,
use
that's
a
what I
normal
thought.
distribution to do it. Yeah. All right. So where are we?
No,
at?
just like the font is too big, bro. But not only the font.
Yeah. So
On the one that
if I'm trying to see if 67% is too low, what would 67% of 250 be? What's that? All right, 160.
7.5.
167.5. So that's what I'm actually looking at is the 167.5. I'm trying to see if that's too low. So the mean I have is 175.
Yeah.
So this is the very last problem, so you should expect it to be a little strange. And the strangeness is that this is not a whole number already. And it's because we calculated it from a percentage of a total, right? And let that sink in. So this does not have to be a whole number, and so I don't have to adjust it because it's already, it's not a whole number. It's not like the probability that it's less than 7 dogs or something.
Like trying to get it as a concept.
So the question was, here's what we know is true from a sample. So we can immediately set up, we can figure out the mean, the standard deviation, we can set this up. Then really what we're saying is this too low? Where do I find that on the picture? These are numbers of households, right? If I remember the problem correctly. Well, yes, internet access and households. So I have to first, I can't use 0.67 on here. That wouldn't make any sense. So 67% of 250, that would be this many households. If that was still true, it'd be here. So now I'm saying, is this too low? So I want to figure out this probability there.
To find the z-score.
Find a z-score, look it up, get the area. Yeah. So that one was definitely a little weird. It's weird because we had to do this, which you normally don't have to do. We normally, the question tells me it's less than 4 households or whatever. So I got the 4 and then I adjusted. This one is, they gave me a percentage. So then I have to adjust that into a number of households.
The stuff we did on the right is just checking if it's normal enough.
Yeah, this was just to make sure we could do this. Yeah, and of course, this we need to get z-scores.
If it wasn't normal enough, we just
couldn't do it. Yeah.
Can I ask you guys an ask you?
Okay.
Okay, so this problem that we did in class, it's like still confusing me because, I don't know, to me like this, it's like you could just like, you would have to calculate like a z-score, so I just don't see why, like, unless is this what triggers it, is when you ask that question, that's how you know?
That's what tells me
Oh,
how
okay, so that's,
because if I want to be, it's all about how do I, if I move further away from the mean, that means my z-score is getting bigger, right? That's the whole idea. So the 99% means I want to be really far away.
No, I got
relates
the
directly
juice,
to
bro.
a
That's
z-score.
French. You
Or a
can
t-score, if I
compare
use a
French.
t-score chart.
Look.
You got 6 best?
So whatever the confidence level is, tells me what my z or t is going to be.
But I do have.
otherwise we're not asking that.
Recording.
Yeah, so this is actually telling you directly, at some point I say there.
Yeah, that's what I'm
So there's no
saying.
question.
So, okay, so that's
Yeah, but if I'm saying what's the probability that somebody watches more than 4 hours a week, all right, that's make it into a z-score, look it up.
Okay. Alright, thank you.
I guess what asking. No, here's a question.
Yeah.
Okay, so this one what I did.